Well, greetings, mathletes, and welcome back. We're going to be talking about graphing quadratic functions today. Now, we talked about this briefly in the past when we were talking about function transformations. It was one of the example functions. So a lot of what we're going to be doing today ties to the function transformations because we will be using them. So let's go ahead and get started. Now, there are two main forms that we're going to be looking at. They get called different things with different books, but I'm going to use the conventions that that your book has. The standard form is often called the vertex form, right? And it looks like this, right? This looks like one of those functions that we transformed, right? X minus h squared plus k. Right, so this is the form that tells us the vertex, and it's called the vertex form. Now, although we're calling it standard form, it's often called the vertex form because of the fact that the vertex is at the point hk. Right, so you can nail down the vertex from that particular form. Now, the other form, your book doesn't give it a name. Sometimes it's called the standard form, so this is why it gets a little bit confusing. In any case, I'm going to call it quadratic form. And it's because it's basically the multiplied out version of this. Like if you wanted to take this and turn it into the quadratic form, you would go ahead and square this, distribute the a, and then add k in, right? So quadratic form looks like this. It's f of x is equal to ax squared plus bx plus c. It looks like the form of the equation in the quadratic formula. So I went ahead and went along with quadratic form. That's what we'll call it for right now. In any case, I'm not going to jump into these right away. One of the things that people had trouble with last time we looked at this stuff was this number a and what to do with it. Right, because A controls whether you have a stretch or a compression and all that kind of stuff. So I wanted to give you a more concrete way of nailing A down so you can get a hold of it. And so we're going to be looking at a function in the form f of x equals ax. I'm taking out all the other things, right? And keep in mind that this A is the same as both of these A's. There's a reason they use the same variable to represent them. And it's because they actually turn out to be the same value in both forms. Now, I want to point out that if a function in the form ax squared is actually both in standard form and in quadratic form, right? If I want it in quadratic form, I can just put in 0x plus 0, right? Because those are sitting there. And if I want it in the standard form, it would be a times x minus 0 squared plus 0, right? And we get the same thing either way. So it's actually in both forms. And we'll be able to deal with it the same way in both forms. So let's take a look at this. Okay, so first of all, the function f of x equals x squared is a parabola. It has the point 0, 0 as one of its points. Then I have the point 1, 1 and negative 1, 1. And then at 2, we go up to 4. Oop, that's 3. Let's just do that. So at 2, we go up to 4. And at negative 2, we're also at 4. Right? And so I end up with a function that looks something like this. There's no point at the bottom. That's actually rounded. I just can't draw. Okay, so in any case, here's what I want you to notice. Let me back some of this stuff up. Let's go all the way back to the first 2 points. Those 2 points right there. Okay, so the 0, 0 and the 1, 1. We know that's going to create a parabola that swoops up. So you can get a pretty good idea of where that goes. Now, once you have that, you really can just sketch it in and just make it match on both sides. So if I have a number that is different than, in fact, let's do this in purple. Let's say I have g of x is equal to 2x squared. So let's see how that changes that. Well, what ends up happening is this 2 tells you where this first point goes. Okay, so now, since it's 2x squared, I still start at 0, 0. Whatever you find as the vertex, that's always where your counting point is. It's just this time it's at the origin, so it's very easy to compute. What I'm going to do, what this number tells me is where I end up if I move one space to the right. So if I move one space to the right, now I'm at 2 instead of being at 1. And so this is a much narrower parabola. Oh, it's a shakier parabola too. Something like that, right? So you end up with a parabola that's much narrower. This actually handles the vertical flip for you too. So let me back some of this up. Okay, if I have something like h of x is equal to negative 3x squared. Okay, again, my first point is at the origin. When I move one space to the right, I need to be at negative 3. So that means I move over to the right 1 and down 3 for the next point. So it's narrower and it's pointed the other direction. And so that handled the flip for you too. Right? If you just pay attention to that. So what's actually happening here is if you move one space over to the right, A is how many spaces you move up or down. It's kind of like a slope, but it's not. Right? Because it only works if you're counting from the origin. If you're counting from anywhere else, that's not the relationship. So it has to be from the vertex, not which happens to be the origin right now. So it's only when you're counting from the vertex that you can do that. You move one space over, and then you move A units up or down, right? You know that's how it's going to work. Okay, so that's the big thing with A. You can always generate a point using A by moving one space to the right and then moving A spaces up or down, depending on whether it's positive or negative. Okay, so that's the first thing. So let's go ahead and clear this off and take another look at all this other business. Okay, so let's look at the function f of x is equal to 2 times the square of x plus 3 minus 2. Okay, so let's just see what we got here. So first of all, we should be able to pick out the vertex. Right? It's going to be the opposite of whatever's by x. So that's a plus 3. That makes this a minus 3. And then whatever's trailing on the end for y, which is a 2. Okay? Keep in mind what's actually happening here. The value, this value here, actually comes from whatever makes this quantity equal to 0. Whatever value of x makes that equal to 0 is what you're actually plugging in there. So just so we're aware of that. It ends up boiling down to just being the opposite. Okay, so we have the vertex. Let's go ahead and mark that. Okay, so I have negative 3. Oops, I'm sorry, that should be negative 2. Yeah, so this one matches exactly. So that one should have that. Okay, and we end up here, right? Okay, so that's our first spot. Now, one of the things we can do, which makes this really, really nice, is that we can use A right away to find more points, right? Because it's the same thing we did before. If I move over to the right one spot, this tells me how far to climb. So that means I'm going to climb to right there. And it turns out to be an x-intercept. And we have the same thing on the other side. If I move 1 to the left, I also move up 2. And that's what that 2 is actually giving us as far as information. At least for parabolas, that's what it tells us. It tells us different things with different types of polynomials, but that's what it tells us with parabolas. And notice that's actually enough information to get a sketch of it already. Okay, but you're going to be asked for more information than this. Okay, you're also going to be asked for what's called the axis of symmetry. And I'm going to abbreviate that as AOS from now on, because that's a lot to write and it takes up a lot of room on the board. So the axis of symmetry, right? Remember that this is x minus h squared plus k, right? The axis of symmetry is h. It falls at h. It's when x equals h, which is a vertical line. Almost said horizontal, right? So that line of symmetry goes straight through the vertex. So whatever the x-coordinate of the vertex is, your axis of symmetry is going to be x equals that number. So we have that now. There are two other things that you're going to be asked for, one of which we already found by accident, but I'm going to go through it and do it the long way. There's also x-intercepts and the y-intercept. Oops. Neither of which are very complicated to get a hold of. If you happen to have an example where you've already found them the way we just did, hey, use them. You already found them. But a lot of the examples don't do that. So I want to show you how to find them if it doesn't come out in another step. So if I want the x-intercepts, okay, it's always the same thing. It's actually the same thing you do with lines. If you want an x-intercept, you make y0. If you want a y-intercept, you make x0. And so that actually works with all functions. It's not just lines. It could be anything. Sine and cosine behave this way. All kinds of crazy polynomials behave this way. If you want a y-intercept, you make x0. If you want an x-intercept, you make y0. So we're looking for x-intercepts first, which means y is going to be 0, and y is essentially f of x. So really what I'm going to do, if I want to find the x-intercepts, is I'm going to take the function and I'm going to set it equal to 0. Now it's quadratic, so you're going to get two answers, right? Which makes sense because it crosses the x-axis in two places. So what we have to do to solve this is strip all the outside stuff off so I can take a square root to get rid of this square. So I'm going to start by adding the 2 over. Then I'm going to divide this 2 off. I'm going to jump up here because I'm going to end up running into that other stuff. So now we have x plus 3 squared equals 1. And at that point, I need to undo this square, so I'm going to use a square root. Now, the square root property will give you, you can take the square roots and you will get an answer, but it won't be complete. Because the way a square root property works, oops, there we go, is that you need both the positive and the negative root. Because, well, let's just take a look at it. So this square root cancels out that square, and I get x plus 3 is equal to plus or minus 1. Now, if it's equal to plus or minus 1, let's think about what that means. I'm squaring something to get excuse me, to move backwards from the bottom, from this step upwards to that step, I would square both sides. And squaring both sides, well, if I square a positive, I get the same answer as if I square a negative, right? So I have to accommodate that there are actually two answers there. And then I subtract 3 from both sides. And since this represents two answers, I can't just subtract 3 from it. I have to look at both of them. So x is equal to negative 3 plus or minus 1. So my two x-intercepts actually happen at negative 3 plus 1 for one answer, and negative 3 minus 1 for the other. So this gives me negative 2 and negative 4. And you notice that's negative 2, and this point over here is negative 4. And so the x-intercept, now you have to be careful because these are actually coordinates. It's not a single number. They would be at, excuse me, negative 2, 0, and 2, 0. right? So I have my two x-intercepts, and that's just basically found by taking the function and setting it equal to 0 and solving for x. That actually works for all functions, not just quadratics, right? Any function, if you want to find the x-intercepts, you set the function equal to 0. Okay, now the y-intercept, well, let me erase some of this because we have a big mess here. I think I need a screen that's approximately 3 times the size that this one is. Okay. Now, if we want to find the y-intercept, well, we said this before, you make x 0. So the y-intercept is actually the easiest way to look at it is the x-coordinate is 0, and the y-coordinate is going to be f of 0, which means you plug 0 into the function to find the y-intercept. So let's just look at what f of 0 is. So it's going to be 2 times 0 plus 3 squared minus 2. Well, that's just an order of operations deal. So now this is 2 times 18. Oops, I'm jumping ahead of myself. I multiplied the 9 by 2 already. So that's 2 times 9 minus 2. So I have 18 minus 2, which is 16. So this thing, actually, it's not even on the screen. The y-intercept is way up there somewhere. So if it's not graphable, it's not graphable, but it is an important point to be able to find. So now that we have that, we have to remember that this is the y-coordinate of the y-intercept. The x-coordinate is 0. So notice, with the x-coordinates, both of the y-coordinates are 0. With the y-coordinate, or with the y-intercept, the x-coordinate is 0. So whichever intercept you're finding, you make the other variable 0, is basically what you want to do. Okay, and it works the same way every single time. But now we have all of the pieces. The y-intercept ended up not helping us a whole lot, but we still have enough to get this sketched. Right? And it should look something like that. Now you are going to be asked for one more item in this. And I'm going to keep the explanation of this specific to quadratics. You know, we found all this point. We found the vertex, the axis of symmetry, and the x and y intercepts. Those are the main things that you want to graph to be able to that you want to plot to be able to graph a parabola. Okay, now you are also going to be asked for the domain and the range. And those are found by looking at the function, right? It's not, I mean, you can do it from the algebra, but it's a bit messy. It's a lot easier to just look at it. So first of all, for quadratics and actually for any polynomial, the domain is all real numbers, which means that you can plug anything into a polynomial function. And since quadratics are polynomials, you can plug anything you want into a quadratic. So the domain is all of the things you're allowed to plug in is the domain. So you may be writing this more than one way. So I'm going to go ahead and do that. Sometimes you just write out all real numbers. Right? Other times, and this depends on how far up the ladder you're going here, but this starts to become a more frequent symbol for all real numbers, which is a double stamped R. So the spine of the R has 2 lines. That means all real numbers. And then the other option is interval notation. And I think this is what your homework's actually asking you for. Basically, the whole number line is all real numbers. And the whole number line, it goes from negative infinity up to positive infinity. You put round brackets on both ends of those, just so you're aware of that. The range is the one that you're going to have to think about a little bit more, because it's what y values does the function produce. Well, you notice if I look here, like let's say I wanted to see if it had a y value at -4. Well, I can see at -4, it doesn't hit anything, which means -4 isn't in the domain. As I move up here, the first place that I hit things is at -2. Okay, and then once I hit -2, I can hit every y value above that because it just goes on to infinity. So that means that the range starts at -2. It includes -2. So when it includes the value, you put a square bracket, and then it has every other value up to infinity. And infinities always get round brackets because you can't actually have a value of infinity. Right? So this would be the range in this case, because from 2 to infinity is basically those are all the values that I can get this function to spit out for me. Okay, so that's actually going through the full thing. We've gone through one full example of graphing a quadratic in the standard form or the vertex form. So I just kind of walk through the steps one more time, just make sure we have them. So the first thing I did was I found the vertex, right? So there's my vertex. I marked that down. I marked it on my graph. Then I used A to count off the next 2 points, right? A was 2, so that means when I move over to the right 1, I go up 2. If I move over to the left 1, I go up 2. That's what A tells me. So I marked those points. Then I went ahead and put in my axis of symmetry. Once you have your vertex, the axis of symmetry is x equals whatever that x coordinate of the vertex is. And so we marked that, and we got our axis of symmetry, which I actually never wrote down. It would be x equals, it's going to be the x coordinate of the vertex. It would be -3, right? So that's our axis of symmetry. Then we go after our intercepts. Now, sometimes you count it up, sometimes you hit the intercept by using A. That actually happens quite commonly. But it doesn't always happen. So if it doesn't happen, you need to find your x and your y intercepts another way. When you want your x-intercepts, you take the entire function, set it equal to 0. Then you solve for x. If you want your y-intercept, you plug 0 in for x. So you find f of 0, and that will give you your y-intercept. And so those are all the steps we follow to go through and graph something that's in standard form. Let's look at one more example here. Okay, so let's take a look at f of x is equal to 3 times x minus 4 plus 3. Okay, so what we're going to do is we're just going to go through all of the stuff we need to find here. So the first thing I need to find is my vertex. Then I want my axis of symmetry. Then I want both x and y intercepts. And that should be enough to graph everything. So let's see what we can do here. Oh, I forgot to put a square on there. There we go. Now it's right. Otherwise, it was a line. Okay, so let's take a look here. The first place we want to start is by finding the vertex. And so looking at this, I can see excuse me, that the vertex is at the point 4, 3. You know, this is -4, but it's always the opposite. So it's at the point 4, 3. Okay, now once I find that vertex, I'm going to employ A to find another point. It'll give me a good idea of what's going on. Okay, so let's see, I have the point 4. It goes here, and I'm going to go up to 3 there. Okay. Now, looking at A, what this is telling me is that if I move 1 to the right, I'm going to move 3 units up. That's what that is telling me. And again, over here, if I move 1 to the left, I move 3 units up for the next point. Okay, so I already have a pretty good idea of what this graph looks like. Now, that also gives me the axis of symmetry. You notice I really haven't done any computation yet. I'm just reading the form. So my axis of symmetry is this vertical line, right? And it goes through the vertex, which means it has the same x coordinate as the vertex. So the axis of symmetry is x equals, and I'm just going to take this 4 off. It's actually that 4 that I'm taking. So that one, you can do both of those without doing any computation whatsoever. Now, x-intercepts. Now, for x-intercepts, I want to make y 0. Now, we can already tell that this thing is going to be moving upwards somehow like this, right? It's going to be doing something along those lines. Where does it cross the x-axis? If you look at that, the x-axis never gets hit. So this is one of those parabolas that has no x-intercepts, and that does happen. However, I do want to show you what happens when you go through the algebra to try to find it, when you look for the x-intercepts when there aren't any. So let's see what happens. So if I want to find the x-intercepts, I set the function equal to 0. So this is now 3 times x minus 4 squared plus 3 equals 0. Okay, so this gives me, I'm going to go ahead and subtract the 3 over. So that's 3 times x minus 4 squared equals negative 3. And then if I divide this 3, I get x minus 4 squared is equal to negative 1. Okay, so now we're to the point where I have the square isolated. That's always the goal with these. Just peel all the pieces off so you can have the square by itself. Then, to get rid of the square, we throw a square root, and we get a plus and minus when we do that square root. You don't want to forget that. So that cancels that, and now I have x minus 4 is equal to, well, this is the square root of negative 1, and we already know that that's I. So this gives me plus or minus I, and if I add the 4 over, I end up with x is equal to 4 plus or minus I. Well, those don't graph on an xy plane like this, right? That's two x-intercepts, 4 plus I and 4 minus I. And I will say there is a way to graph that, but not on a graph like this. You actually have to do something kind of special to be able to graph these things with complex numbers. So later this semester, we will be looking at how to graph a complex number. So that will come into play, but we are not there yet. If you get complex answers for your x-intercepts, that means there are no x-intercepts. It's a 0 of the function, but it's not an x-intercept. So that means there's none here. Now, if we want the y-intercept, and I'm going to go ahead and erase this here. You can always rewind and pause if you need to copy it. There will always be a y-intercept. There's never a time that there's not a y-intercept. Sometimes they're not graphable because they're too big of a number, but there's always a y-intercept. And you're going to find that by plugging in 0 for x. And since I'm plugging in 0 for x, that means that the x-coordinate of the y-intercept is 0. This gives me 3 times 0 minus 4 squared plus 3. So the square of negative 4 is 16, so this is 3 times 16 plus 3. 48 plus 3 is 51. So the y-intercept is at 0, 51. And clearly that is not going to fit on this graph. And that's fine. You should still know where it is. Okay, so we have that much. Now we need to talk about the domain and the range. The domain it's all real numbers, right? Or I actually prefer this symbol because it's so much easier to write, but that's okay. Now the range we have to think about a little more. It opens up, which means it's going to positive infinity. And if it's going to positive infinity, it must have a minimum value somewhere. And it looks like that minimum value is at 3. Notice that minimum value is that value, right? It's just something to note. If the parabola turned out to be pointed down at this point, then that would be a maximum value. So now the range, it looks like it starts at 3. Oops, it includes 3. And goes off to infinity. And just so you have an idea of what it looks like, if I had something like this where it went down, right? If I was looking at something like this, the range, you always write the range and the domain from smallest to greatest values. And so in this case, we have a maximum value at 2. So the range here would be from negative infinity to 2. Whoa, that's terrible infinity, but looks like the 8's still falling over. But yeah, so if you have a maximum value, then that value comes second, because you always go from smallest to biggest. You're always counting these things upwards. So whatever you hit first moving upwards, which I guess would be negative infinity, that's what you write first. Okay, just so we're clear on that. Okay, so let's go ahead and clear that off. There we go. And okay, so let's go ahead and take a look at one of these in quadratic form. So we have f of x is equal to x squared minus 4x plus 5. Now, I want to point out something. It's not going to be the way we're going to do this, but when you have something that's in quadratic form, oftentimes it's a lot easier to graph it when it's in the standard form or the vertex form. So completing the square is the process that you use to go from one form to the other. So what we can do here is go ahead and complete the square. So let's see here. That means that if we're going to take half of the middle term, so that's half of that makes negative 2, and I square it, so that makes that a plus 4, but then I have to add a minus 4. So this should be a perfect square, and it comes out to x minus 2 squared. And then if I add the 4 and the 5, I end up with a plus 1, right? And so we've transformed our function into the vertex form. I can see clearly from there that the vertex is at the point 2, 1, right? Okay, so you can, if you just complete the square on this, you can turn it into the other form and use all the tools that we got with the other form. Okay, so I just wanted to point that out to start with. That's not how we're going to work this out, though. We are going to take this and actually deal with it in the quadratic form, one thing at a time. So the first thing about the quadratic form is that it's actually, we're going to go after the things that are the easiest to find first. So one is the y-intercept, right? We find the y-intercept by making x 0. It would be f of 0. Well, you notice if I plug 0 into the first two terms, it just kills them both, right? Because 0 is a multiplicative assassin. Anything it touches, it kills. So those first terms are irrelevant, which means that just like a line, that number hanging out on the end, that constant, is your y-intercept. So that means we have a y-intercept at 0, 5, and I haven't even done anything yet, right? So the next thing I want to find is my x-intercepts. Okay, now you find the x-intercepts the same way we did before. You set the function equal to 0. And I'm going to do this over here underneath the graph. So let's see, we got x squared minus 4x plus 5 equals 0. Now, here's the thing. That's a quadratic equation. So you can use the quadratic formula. You could complete the square to solve it. You could see if it factors. So you have a bunch of choices here. It actually turns out that this doesn't factor. So we're going to have to do something else. I like to use the quadratic formula with this because it actually gives you more information than just the x-intercept. So let's take a look here. So if I use the quadratic formula, it should be x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Right? And then a, b, and c are just the respective coefficients of x squared, x, and your constant term. So we just need to plug it in. So let's take a look at what we get when we plug this in. So negative b, let's see, if b is negative 4, so negative b is positive 4, plus or minus the square root of b squared, which is 16, minus 4 times a, let's see, a is 1, times c. C is 5, and that's all over 2a, and a is 1. So that's over 2. And we just need to simplify this down now. So that inside actually simplifies it to -4. Okay. And then we can go ahead and simplify that root there. That the square root of -4 is 2i. So this is 4 plus or minus 2i over 2. Now we can separate this out over this denominator of 2. So 4 divided by 2 is 2 plus or minus. And then 2i divided by 2 is just I. Right? So we just simplified that down. Now, here's what's really nice about this. There's a reason. I mean, we were going to get a complex number, which means there aren't any x-intercepts at all, right? We got a complex number. If we got real numbers, then those two real numbers would be each of the x-intercepts respectively. So there are no x-intercepts, but it was worth us going through this anyways, because it gives us the next answer. The next thing we would look for is the vertex. Right? So we want to find the vertex. Well, here's what's really nice. When you look at the quadratic formula, right? So here's our quadratic formula over here. The real part of the quadratic formula, right? The part that's guaranteed to be real no matter what, which is, let's see if I can circle this without getting all over everything else. Which would be this part right here. Right? Everything except the square root part of it is actually the formula for the vertex. Right? So that means that the real part, or not the real part, but that first part of your quadratic formula, that piece, is the x-coordinate of your vertex. So we found that now. Right? We need the y-coordinate. Well, that's the problem. We have to figure that out. Well, I know that it's a function, and so if I have an x value, all I have to do is plug it in to find a y value. So I'm going to take that 2, and I'm going to look at f of 2. So what it's going to be is whatever f of 2 is. So if I plug 2 in here, that ends up with 4 minus 8 plus 5. Right? So that gives me -4 plus 5, which is 1, which means that my vertex is at the point 2, 1. So that's actually really convenient. Right? So let's look at what we have so far. I have a y-intercept at 5. I have a vertex at the point 2, 1. Okay, that means that my axis of symmetry has to have the same coordinate as the vertex, as the x-coordinate of the vertex. So my axis of symmetry is x equals 2. So I can draw that in. Here's where the axis of symmetry is actually quite useful. Oh, there we go. Over here, at this point where y is equal to 5, I have a y-intercept. But this symmetry line actually tells me that there's another point that is 2 units on the other side of the thing, of the axis of symmetry, that is also a member of the function. Right? So you can reflect, if it's 2 units this way, that means it's also 2 units this way, as long as you stay at the same height. Right? So I'm generating another point there. The other thing that you can do to generate more points is to use A. Since A is 1, that means when I move 1 unit to the right, I move 1 unit up. Same thing with 1 unit to the left. And so now I have enough points to graph this thing. Now keep in mind, I'm giving you a lot of different points to use for graphing. You don't necessarily use all of them, but you will be asked for the vertex, the axis of symmetry, and your intercepts. Those are things that you're always going to be asked for in these questions. And then quite often you're going to be asked about the domain and the range also. So let's go ahead and take a look at that. And as a matter of fact, this is a good place just to kind of test yourself if you want to pause the video here and see if you can figure out the domain and range on your own. Okay, so domain Um, the domain is basically anything you can plug into the function, which is all real numbers still. The range are all the possible y values you can get out of this. And I can see that since this opens up, I have a minimum y value at 1. Oops, I keep doing that. I keep making round brackets instead of square ones. Easy thing to do. Watch out for it. Even your professor's making that mistake. Okay, so the range starts at 1, but then it goes up all the way to infinity, right? And we end up with our domain and range this way now. Okay, so let's just kind of look at everything we did. Okay, so the first thing we found, because it was the easiest thing to do, was the y-intercepts, right? I went after the x-intercept, and there's zeros of the functions, but they're not x-intercepts because they're complex, right? So as soon as you get complex numbers, you don't have an x-intercept. But even though we don't have an x-intercept, I can use the real part of this complex number to generate the x-coordinate of the vertex. And that actually also gives me the axis of symmetry, right? So I want to point out a couple of things here. I just realized I didn't put the formula down the way I wanted to. But anyways, once we have the x-coordinate of the vertex, to find the y-coordinate, you plug it into the function, right? And then whatever value you get for that is your y-coordinate. Domain and range, you look at it, right? And try to figure it out from there. Now, I do want to formalize this a little bit. So I'm going to pull this apart, but I'm going to erase this. I'm going to back up and just look at this from a formulaic standpoint. Okay, so let's just say in general our function is f of x is equal to ax squared plus bx plus c. Okay, now first things first, the y-intercept, well, you're looking at it. Whatever c is gives you your y-intercept. It's the point 0, c. Okay, now x-intercepts. Basically, you set it equal to 0 and solve the quadratic formula, right? So if you want the x-intercepts, and I'm not going to say how you do it, but you want to solve ax squared plus bx plus c equals 0. So that could be quadratic formula, it could be completing the square, could be factoring, right? Now, for the axis of symmetry, which we actually found before we found the vertex, right? It turns out that the axis of symmetry is just that first part of the quadratic formula. It's what you would have used when you found your x-intercepts. It's the part that's negative b over 2a, right? You notice it's all, the only thing it's missing there is the square root, right? There's no square root, the plus or minus the square root of b squared minus 4ac. It's just not there. But that's what it is. So that's your axis of symmetry. Your vertex, well, whatever the coordinate is here on your axis of symmetry is the x coordinate of your vertex. Oh, I wrote down the answer from the last thing. We're doing this in formula. So the x coordinate here is just negative b over 2a. You don't got to plug it in again because you already have a number in your hand. And then the y-coordinate is just taking whatever the x-coordinate is and plugging it into the function. And it looks nasty because it's in formulaic form, but keep in mind, negative b over 2a is a single number, right? It's not a formula you have to plug in and chug away. So in any case, these are the main things that you have to be able to find. And then from the picture, you find the domain and the range, right? The domain's always all real numbers. That's pretty much always how it works. Okay, so those are the big formulaic pieces of this. Now I want to take a look at something else here. So let's go ahead and delete that. Okay, So this example, let's take f of x to be negative 3x, 3x squared plus 6x plus 2. Okay, now it's not a bad idea to pause right here and see if you can walk through this entire problem. All the formulas still work. And actually, what's kind of nice about using the formulas is that they work. You don't have to feel your way around anything. You can just go straight to formula and plug things in. Although it is a little faster if you use other methods. But let's go ahead and get started on this. So we want to graph this, and then we want to find its domain and range. Okay, so just some things to note right off the bat is I have a negative out in front. A is a negative number, which means that the parabola is going to be opening downward, right? Which means that the vertex is going to be a maximum point. Okay, so let's just go ahead and start at the top with the y-intercept. Okay, well, if I make x 0, the y-intercept, well, that's going to kill the first two terms and just give me a 2. So I know I have a y-intercept right there at 2. Okay, so now we'll turn to the x-intercepts. And actually, I know I'm finding the x-intercepts, but the process I'm following is actually going to allow me to find the axis of symmetry and prepare to find the vertex at the same time. Right? So let's go ahead and start. We have, I'm just going to start it over here. So minus 3x squared plus 6x plus 2 equals 0. So we are dealing with this, using the quadratic formula. Now, one of the things I find that always puts me off when I'm dealing with the quadratic formula is if I have a negative out in front. I'm going to go ahead and keep it for right now. You can always massage these when you're looking for the x-intercepts and stuff. Because it actually does change the function to a different function for the moment, but it has the same x-intercepts. In any case, so I know that the x is going to be equal to the opposite of b, which is negative 6, plus or minus the square root of b squared, so that's 36, minus 4 times a times c. Well, that looks like a lot of fun. And the whole thing's over 2 times a, and a is negative 3, so this is over negative 6. So we just need to simplify this root. Oh, I wrote 36 squared. 36 is the square. I don't need to square it again. Yeah, 36 squared is like 46,656, I think. That's going to be a little bit of a big number. We're not going to do that. We're just squaring 6. Okay, so let's see what we have on this other side here. Let's see, that's a negative, negative, so that makes that positive. That makes that a 24. So this is 36 plus 24. Is that right? Yeah, so that should make it a 60. So let's see here. So that gives me negative 6 plus or minus the square root of 60 over 6. Now, I do want to point out the axis of symmetry is staring us in the face right now. You can actually peel that out. It's the part that's not in the square root. The negative 6 over 6 means that the axis of symmetry is at negative 1. Right? Oh, wait, that's the denominator's a negative 6 also. Excuse me. Negative 6 divided by negative 6, right? This piece right here tells me that the axis of symmetry is x is equal to positive 1. Sorry, I said negative 1. I forgot about the 6 in the denominator. That's part of the reason I don't like to deal with that with a being negative, because I always forget about the denominator. Okay, now, for the rest of this, though, we have to simplify the square root of 60, right? And so let's see here. What goes into 60? I'm just going to step to the side here and factor this. 60 is 6 times 10, 2 times 3, 5 times 2. So it looks like the only thing we have in common here are the 2's. So this is now negative 6 over negative 6 plus or minus 2 root 15, right? Because the 3 and the 5 still get multiplied together over negative 6. If we simplify this now, this ends up being 1 plus or minus, let's see, 2 and 6 cancel, so that makes it the square root of 15. And actually, since I'm doing one positive, one negative, I can just keep this as positive because if I multiply this, it just ends up changing the top one to a negative and the bottom one to a positive. So it works out the same way either way. But this ends up being my x-intercepts. Now you notice this part right here is my axis of symmetry once again, right? I end up with it over here again. So now, how do you write these things, right? There's two ways to write it. You can either separate it out like that, or you can keep it together. It should accept it both ways. So the two x-intercepts are going to be 1 plus the square root of 15 over 6, comma 0, because when you find an x-intercept, the y-coordinate is 0. The other one would be 1 minus the square root of 15 over 6. Oops, parentheses too soon, comma 0. Right, so those are your two x-intercepts. Those aren't very convenient to graph, are they? Right? You know what they are. They actually are important, and they end up being important for other things. But let's go ahead and fill the rest of this out now. So now I know I have an axis of symmetry at x equals 1. Right? So I know the axis of symmetry is there, which means that the x-coordinate of the vertex is 1. So I need to find that now. So let's see. If I plug 1 into the function, right, I need to find f of 1. Well, that's going to make these x's into 1's. So it's negative 3 plus 6 is 3 plus 2 is 5. Right? So this is at the point 1, 5 now. And I did that just by plugging 1 into the original function. So now I have, let's see, that's 4, that would be 5 right there. And I want to point something out here. Remember we talked about this number a helping us find other points. Well, that means if I move 1 space to the right, I have to move down 3 because this is a negative 3. So I can find another point just by starting at the vertex, moving 1 to the right and dropping down 3. Notice that if I do it in the other direction, that gives us my y-intercept. It's coincidence, but it happens. Now, as far as your x-intercepts go, when they come out to be irrational like this and they have square roots in their answers, they become very difficult to graph. So if you need a decimal approximation, plug this into your calculator and see what it spits out. But honestly, you should have a vague idea at least of how these things fit in here. Right? It doesn't have to be exact, especially if you're plotting in my math lab. You just have to make sure that you have enough points to get it close. Incidentally, plotting parabolas in my math lab. I just thought about that. Okay, so yeah, we have everything here. Yeah, let me clear this off and talk a little bit about how to plot in my math lab. Okay, so here's an example of what one of your homework problems might look like. We can enlarge the graph a little bit, but I just want to point out how the parabola tool works. So you have all these tools on the side for graphing things. You have an absolute value tool, a line tool, circle tool, and then I have parabolas that open up and down and parabolas that open sideways. All of our parabolas are going to open up and down to start out with. This is how you graph. The first point you need is going to be the vertex. Okay, so you mark the vertex. The second point is any other point that you know is on the parabola. So a y-intercept, some point that you found by plugging in a number, anything, because as I pick this second point, it changes the shape of the graph. So once you pick it, all you have to do is click and it sets it in place. Right now, this is going to be wrong because I'm not even looking at the actual function here. I'm just graphing this just so you can see kind of what's going on here. So if I clear it, cancel, oh, clear, okay. I can also, if I, oops, try it again. If I hit the first point, I can open this downwards. If I just click a second point that's downwards. So I just wanted to make sure you saw how to do that. I'm not going to work out any homework problems or anything. I just wanted to make sure you saw how to graph these things. So in any case, those are the main things I wanted to get through today. And so our next adventure is to generalize these graphing strategies to all polynomials. And actually, that's pretty much what the rest of the chapter is how to deal with these things on all polynomial scale. So in any case, until next time, keep your pencils and your wits sharp.